Professor Borth, or Damian, is a professor in University of St.Gallen in Switzerland, and by happy coincidence, or maybe it's not coincidence, he was also on the jury of my PhD defense. So I'm very happy to see him again. And also on actually the day of my defense, he gave a very interesting talk about learning representations for neural network model weights. The general idea and some of the work they've been doing, and I found it super interesting. So I'm very happy to see that today he will be presenting that line of research, but applied to geospatial representation specifically. So very curious about that. Yeah, I will keep the introduction very short. So Damian, please go ahead. The floor is yours.
Yes, thanks a lot. Thanks a lot, Ruben, for the invitation. Great to see you again. Anything else? Or
sorry, I just realized that I have to still put the presentation on a large screen, but it just worked. So I'm very sorry.
Yeah, just magically. No, again.
Yeah. So go ahead.
Thanks a lot for the invitation. Thanks a lot. Very much appreciated. Also great to see you again. And this is quite interesting. This is kind of a follow-up presentation of the presentation that I gave at KU Leuven. Nevertheless, it's quite nice because it brings the two areas that my research group is working on together for the first time. So it's a very special moment for me presenting this work for the first time. It's currently under review, and it's a collaborative work with Joel Hanna, Damian Falk, Stella Yu, and myself. So Joel is just finishing a PhD. Damian just started, so it's a great setup. And the name is GeoSANE. We will hopefully know after the presentation what SANE stands for, learning geospatial representation from models, not data. So that's the overall setup. To start, I'm quite interested and think it kind of interesting to see when we look into the different artifacts in machine learning, where is the information or where is the knowledge stored. So that's quite interesting. If you look at the traditional setup, it is in the data, right? The data, the pixels itself, or the multispectral, hyperspectral data has information stored, and this is a lot of research is being done here about different data sets and how they are similar to each other. Can we extract this information or distill this information? Can we actually synthesize data and therefore take from an original data distribution its characteristics into a synthetic distribution? So there's a lot of interesting research that is happening on the data sets that we are all using in machine learning. There's a second area, which are the model parameters. So this is quite interesting. If you look at what we are currently doing, we are taking actually the information and knowledge stored in the pixels and the data and compress it into the weights of the neural networks. This is done traditionally through backpropagation and optimization on a loss landscape. And the question that I think is very interesting, like how much information can we extract from the weights of neural networks? And, people are doing this for a long time. They're thinking about, do we need all the weights? Can we actually, prune some of the parameters? Can we make smaller models, right? Can we infer from the weights in which data set was the model trained on? And all those interesting questions like model compression and knowledge distillation. And recently moving more and more into the focus is more like the question about the context. So this is the classical language model in context learning, where forward pass is not only depending on the weights of the model, but very much on some kind of additional information in RNNs that might be a hidden state that is processing a sequence. For attention, that's a contextualized vector that is changing the activations. And classically, we all know this from the prompts and the prompt engineering that is being done, where we can change the output of the individual, models that we're using. And if you think about that, I believe that these are not three distinct things, but rather there's a continuum that you have from, the data set on the one side and the information moving from the data set to the model parameters, and maybe from the model parameters through the contextualization of a prompt to, the in-context learning. So you can think about this as a continuum. And there's also a lot of research happening if you think about remote sensing or Earth observation. Just classical, we take a data set, we distill, or we train a model, but also recently reasoning on top of embeddings. You could also think as an example of something here in this direction, where we contextualize through prompts the inference on embedding states through models. Today, in this talk, we're going to focus on the model parameters, which means the compressed knowledge of the neural networks in the weights and biases of those neural networks. So you can think about this, and this is, an interesting new neural artifact that people are thinking about. And we started, looking at this in my lab around 2020 with some publications, 21, and other people started to work on that. We, collaborated with many people, and then in 2024, actually, we met all the people coming from kind of the, weight symmetry area, from the learning area, from some visualization inference area came together, and we recognized that we all actually working on something very similar, which was this moment here at ICML 2024. And then, we started to think about this, is this a new community? And this entire thing was, coined weight-based learning. So can we learn from the weights if we consider the weights of neural networks being a new data modality? So being a new input for representation learning. That's, what we understand under the term weight-based learning. And I think it's actually very interesting to consider not only pixels or language being an element, or time series data being an element to train the representations on top of that, but very much, the weights itself, which are actually structured because they are representing a particular computational graph that is allowing us to perform inference on the samples that the models are trained on. And this moved forward. We had a workshop at ICLR 2024, and more people came together, and now this community is growing, and it's really, really interesting to see how, in which directions the different areas are going. In general, if you think about that, weight-based learning, the idea is to learn from populations of neural networks, and in particular, the models and the weights. So if you look at that, you could think about neural networks. There are quite some challenges, right? They are very successful in multiple domains, as I mentioned, textual data, pixels, multispectral data, time series data, etc. But there are actually a lot of headaches associated with training neural networks. There is this problem of this non-convex loss surface during the optimization. You have a very high dimensional space. If you think about weight space, that's the space of all parameters of the models, which is at current large language models, with its billions of parameters, a very high dimensional space. So it's kind of very difficult to do something in that space. And it's actually, neural networks are highly sensitive to initializations and, parameter settings. There's also very interesting research going on currently with, phase transitions, something that you can see here, where depending on how you set up your parameters, you might end up in one of those phases that are beneficial because they're generalized, or are non-beneficial because they might overfit or underfit, and it can guide you in how to set up a proper model, or visualize and indicate effects like grokking, where you see a network is kind of overfitting, but if you continue training, is actually moving forward, and after some time is able to generalize. So it's interesting things that are happening in this area of neural network or neural network research. What I again think is interesting is that we have on the one side the structure of the neural network given its weights, and this is very high dimensional weight space. And on the other side, we have actually the behavior of the neural network with regard to its functional performance, to its latent generating factors. And I kind of think it's very interesting to kind of connect those two worlds and trying to understand how the configuration in weight space, the neural network's configuration, is related to these characteristics. And basically, if you think about that, it is about populations and not so much about individual neural networks. So this entire weight space learning area is kind of motivated by that we have populations. You can think about populations of neural networks that, in general, we would have our ingredients to train a neural network, some type of data set, we would have some type of architecture, and then we would have some type of hyperparameter that are actually giving us the protocol how to train the neural network, what kind of optimizers, and initialization, learning rates, etc. And if you put this together and train the neural network and invest the compute, then usually you end up with a model. But what happens if we actually take this idea and generate a population of models? Given the non-convex optimization and the variability of the hyperparameters that we can choose, we could think about that there is, when we retrain this single model, that there is a population of neural networks all trained on, let's say, fashion MNIST with the architecture being a ResNet. That initially doesn't make sense because you would not train 100 or 1,000 models for the same task and the same architecture. But the underlying hypothesis is that if you do this and you have this population of neural networks, you might learn something really interesting about those neural networks. My initial feeling is that, and hypothesis, that these neural networks, they are not randomly in weight space. They are structured, and given that they all kind of follow with a particular task, the structures in weight space are encoding the information of those neural networks that are trained. So that's the hypothesis that we were able to, in our first works, to show. The weight space is not random. There are actually these structures and they contain useful information. However, it's still very high dimensional. So the idea would be that maybe we could take now this high dimensional weight space, take the weights of those models as input, and train actually a lower dimensional representation. Thinking that those structures, those lower dimensional embeddings or manifolds, that they are actually making sense with regard to the models that have been trained. And given that lower dimensional representation, it would be actually really, really interesting if each of those neural networks, for example, colored here, you have this neural network that is red, you have this neural network that is yellow, that these, once embedded in this lower dimensional space, in this learned representation space, are points in this space. And if you, for example, would have a training trajectory of, you train your neural network for 50 epochs, you would have a trajectory like this little spaghetti here in this representation space. So that's kind of this idea that can we embed the population of neural networks into a lower dimensional manifold? And the idea, once we would be able to do this, we could take a new neural network that comes somewhere, right? We have no information about this neural network. We could take it, we could move it into this representation space, and given that this representation space encodes meaningful information, infer properties of these neural networks, or use this lower dimensional representation space to do other things. To be able to do so, we need to have some way of learning those lower dimensional representation or lower dimensional manifolds. They have to be meaningful, best case smooth and nice behaving, so we can navigate, traverse those spaces. And hopefully they are preserving the information that those neural networks have in the original weight space. So that's the idea on a very abstract level. And once we have this, we could use actually those learned representation spaces for many useful downstream tasks. One downstream task could be to use this representation space for model analysis, right? We could run diagnosis, we could predict accuracy. We could think about maybe some kind of fingerprinting neural networks to do identity or versioning on neural networks. Another idea would be, since we have, in our, populations, maybe training trajectories, we could learn about learning dynamics, maybe learn how to, new stopping rules or early stopping rules for training. We could do population-based model selection. If we train maybe, with 100 models for 5 epochs, maybe we could predict if some of those models are great learners and others are already in areas that are not very successful. So we could stop training half of the population and continue training with the other to save compute and energy costs. Or if, we would have a well-behaved latent space, and this latent space could be, is meaningful, we could sample from that space and through sampling generate new model weights that could be put into, new neural networks without, the computationally expensive backpropagation optimization procedure that we all used to. This could be used for initialization, transfer learning, meta learning, sparsification, many, many ideas. So this slide is about kind of an idea of what weight space learning, in particular, when you think about populations, could do. And we have already a couple of ingredients. We need a population of neural networks. We need something, a learning backbone that allows us to learn meaningful representations. And then we have some downstream tasks. So some, or I would say some of those things that I have listed here on the right, people were able to already accomplish, predicting accuracies, thinking about early stopping, or do model sampling. So that's great. Some of those are still, ideas what you could do once you understand there is this lower dimensional space you could use. So that's the overall setup of weight space learning. And one more thing, which I think is really, really interesting, is that if you think about the way how you would turn a neural network into actually an input, think about you have this kind of population, right? They're all trained with a data set, they're all trained with some setups, architectures, and you have this population. The way how we process those weights is we stripe those weights away from its architecture and vectorize its parameters in a very naive way, right? Just create a very large, very long vector. This can be for, ResNet's 10 million weights, 20 million weights. It can be for the large language models, billions of weights. So this is a very naive way of doing that. And you can think about that the weights of the neural networks in this vector are a sequence, right? And there you can think about, transformers being used as the underlying learning backbone. Weights, however, they have a very special characteristic that is different to pixels and actually words. They have this, setup where you have a model, you have this computational graph, you have the model parameters. They represent a function that allows to map from inputs to outputs. And what neural networks and its weights have is that there is a lot of, symmetries in weight space. You could think about a very simple thing, like you have a neural network taking one layer, and if you would swap one of those, the green neuron with the red neuron and swap actually its weights, you would have actually the same neural network, the same functional, representation of the network, the same function. However, for us, if we would naively stripe away and vectorize the weights, this would be a different vector that is representing this neural network. So we would have two vectors that are actually from the same function, but they're differently. This can be a disadvantage because there are a lot of permutation symmetries in weight space. And there are a lot of people that do great work about learning equivariant encoders into this latent space that are, taking care of that. For us, it's an advantage because in our learning backbone, we have to deal with augmentations. And one of the augmentations that we're using, because we have a contrastive loss, is this permutation augmentation to create a positive sample to the original sample to create the contrast with negative samples. So there's an interesting, way of thinking about weights being data, and there's much more about that. There's great work here in this paper about all that, and you can think about other augmentations and symmetries with regard to scale, given that the activation function is a ReLU and all those things. So I gave you now a little bit of an overview about weight-based learning and the ideas. So the big question is like, but what does it have to do with remote sensing and Earth observation? And at the end, we're here for remote sensing and Earth observation. So how does it connect? And if you think about what currently, a lot of, in the last years, happened in remote sensing and Earth observation, is that, previously, when I started in this area, we had this setup where we had this kind of, people were training very specific, specialized, task-specific models that were solving remote sensing and Earth observation tasks like the flood detection, land use, land cover classification, or other things. And you had, small ResNets that were doing very, very well, and you could use them. Then, the era came of foundation models. People started to train large task agnostic foundation models that you could take and then fine tune actually to the task specific versions or variants of those models. So currently we have a setup where there are many of those foundation models. We have approximately 70 and more foundation models given the latest survey papers. So there's a lot of foundation models. And if you take each of those foundation models and think about that, you could fine tune those task agnostic backbones to the specific task, you have a lot of models. So there's this kind of, explosion of models and in remote sensing. And it can be very difficult to kind of understand which models to use and which models, are good for which tasks. But when I'm looking at that from my weight-based learning, glasses, I see here, we have model zoos, and these model zoos are growing. We not only have this, specialized models that are living on, pages or platforms like GitHub or Hugging Face, but we have foundation models, and we have actually a lot of, specialized models that exist in that area. So the question would be, can we take actually all this entire population of remote sensing and Earth observation models and take this and extract their knowledge, force, weight-based, with the idea of weight-based learning into one representation where we can then sample models on demand. Because the one thing that in remote sensing is getting a little bit more difficult is, in particular for partitioners, in the past, partitioners were able to take those small models that are highly specialized and deploy it in the field. Currently, if they want to do, perform a task, a VIT model with 400 million parameters, which is then much, much larger than the ResNet, when they fine-tune that, they have to carry those parameters with them, right? So those large foundation models are great, but they are actually very challenging if you want to deploy them on, satellites where you have little storage and little compute or somewhere else. So you always have to carry this large model. So it would be actually really interesting if we could train a representation where we could sample models on demand. Large models or small models or something in between, all from the same representation. And this is exactly the idea that, GeoSANE is proposing. So the idea is to learn, from models and the weights and not from data. So what we have currently is this data-centric pre-training of geospatial or remote sensing foundation models, where we take all those beautiful, data sets that are out there, multispectral, hyperspectral. We train this very, strong task agnostic backbone, and then we fine-tune towards whatever downstream task modality we are aiming for. And what we actually propose is to take not the data, but take all those models that exist on those platforms, learn the representation, as previously mentioned, and then sample your model on the go. And sampling in this world means a forward pass through the decoder, a very cheap forward pass as compared to doing an expensive pre-training. So instead of getting a new foundation model out, we can actually harness or hopefully harness the knowledge of all the foundation models that are out there. And this is exactly what we propose with GeoSANE. So GeoSANE is this idea to take a large population of models. We have platforms like Hugging Face where we can download those models, ResNets, units, VITs, detection, swim transformers, vision language models. Download everything, right? The more, the better. Have a representation learning backbone. Here we're taking these scalable autoencoder for neural encodings, manual embeddings. I will go into the details that takes actually this kind of vectorized vector of weights from each model, adds a position encoding, tokenizes that, and then moves through multiple blocks of transformers with a compression layer to learn this shared latent representation, decompresses it, and moves through the decoder blocks, and then brings those tokens back into the weights. Then you have the original weight sequence, you would have the reconstructed weight sequence, and you can learn with a reconstruction loss or learn with a contrastive loss with the augmentation that I have mentioned previously. This is unsupervised. This means we don't need any data. We only take the models, which is for us important because there's a huge fraction of models on platforms like Hugging Face that is not documented very well. Up to 30% is not documented at all. Some models are very well documented, all the language models. For others, sometimes is a great documentation. Sometimes there are huge gaps in documentation. So therefore, this unsupervised setup is very important. This is learning entirely on the weights itself. And once we have trained this backbone, we can take the decoder and use the decoder to generate new weights. We take a model prompt. This could be VIT trained on ImageNet, like something that many people do in the remote sensing foundation model world. Take this, we put this, encode this through the encoder to point into the latent space. Sample, I will go into more details how this looks like in that latent space, and then move those tokens that are sampled through the decoder. Right, we take this, we embed this into the latent space, learn a KDE, a kernel density estimation distribution around that, sample from that latent space, and then decode into the models. So this would be the idea on a very abstract level, and let's go a little bit more into the details. So we have a little bit of background noise here. Okay, so the first step is to get a model zoo of remote sensing models or remote sensing Earth observation models from actually Hugging Face. So we did this, we created, keywords. Hugging Face is really nice, so you can query actually the metadata, and there's a list of keywords that we used, whatever we thought about. We took this as input and queried actually Hugging Face, the website, and we downloaded 100 models with some are very small, some are very big, with billions of parameters. So if you think about 100 models, doesn't sound a lot, but if you compare it to the weight sequences that they have, it's a lot of data. Billions of parameters comparable to other setups where you train from pixels or from words. And if you look at that, we have a following distribution. We have not stratified, but some distribution around ResNets, VITs, swim transformers, vision language models, YOLOs, UNets, and kind of the kitchen sink of other models that we have here. So there's a good distribution of different architectures. And we have some are foundation models, some do specific, so task agnostic or specific downstream tasks, given that hopefully the metadata documentation is correct, object detection, flood detection, vision language, and others. So it's a kind of a very heterogeneous model zoo that is different in architecture and different in modality and the tasks that those models do. So we have our model zoo. That's great. Now we need the representation learning backbone. So I would jump a little bit more into the details. So what we have previously done is an autoencoding transformer. The autoencoding transformer takes actually the whatever convolutions or fully connected layers or matrices for key value query, tokenizes that. There are different ways how you can tokenize that. The details are all in the papers. Either you tokenize by weight metrics, you tokenize by the individual weights, then you generate tokens, you add position encoding, position within the layer, position in the overall position of the network, and encode that on those tokens. Then, you move this from multiple of those transformer blocks. In the, simple autoencoding transformer, we had then one embedding, one point in latent space that we then moved back through the multiple transformer blocks. So here we had 8 transformer blocks, and detokenizes and then reconstructing on that, and with that and the gradients, updating the weights of the decoder and encoder. So that's our first method, which was actually restricting the sequence length. So this is not scalable, but restricting. You only could do like model sequence length that are fitting in the transformer and the compression layer here. So small models. We then updated with GeoSANE, the sequential autoencoder for neural embeddings. The idea is that you learn, tokens, multiple tokens that are compressed. The compression layer is actually very important. You decompress, you move back and reconstruct. So the same setup that we have in the original autoencoding. And the trick is here that we also generate a contrast or use a contrastive loss on the latent space to group actually good performing model from bad performing model, or to group similar architectures from different architectures. And then we could here scale with the model size, because once we have this setup, we can think of larger models as a sequence of tokens, and therefore process as a sequence or a windowed sequence of tokens with our representation. This is very similar. I mean, it sounds a little bit complex. It's very similar to what language models are doing, right? They don't try to learn the entire book, but they try to learn sentences that are moved through the representation. So you can think about a neural network is a book, a layer is a sentence, and a weight is a word. And this is the way how we are learning here. However, this is not autoregressive, but we have this reconstruction through the compression layer because we want to have lower dimensional manifold that we're learning. So it grays for this case to larger models. Up to today, we are able to do VITs, and we're starting to work on GPTs, GPT-2s as the first. We have different models. They share all the same embedding space. However, the original GeoSANE, given that there is some normalization, is not working on heterogeneous zoos, but rather on homogeneous zoos. So you could only work on zoos of the same architecture. They can be trained on different data sets, but it's homogeneous zoos. So we had having the idea to train on populations that are very diverse, as the one that I showed in the previous slides on Hugging Face. We need to change a lot of internals and totally change the normalization, the tokenization to move to GeoSANE. That's a little bit of the inertia and the learning backbone. And now how do we sample? Well, we take actually some models that we have. They are considered, we consider them a model prompt. We use the encoder to point into the space, learn per dimension KDE, and then sample individual models out of that. And you can think about this also as a procedure that can be actually bootstrapped, right? Because the very moment you sample from the latent, that's a forward pass. That's very cheap. So you can generate 100 models, check which models are good, take the top 3, their position latent space, and explore further 100 models from those positions with the KDE learned, and generate again. And you can bootstrap that multiple times and refine. It's actually pretty interesting, how you could explore and also do latent search or latent optimization on this latent with original data. So last but not least, the goal is to sample model, and therefore we need some sanity checks that we did in some previous work. Let me introduce those to you. So think about, you have a latent space. How robust is that? This is an autoencoding transformer that works on sequences. It's not a variation autoencoder, so there's no imposed underlying structure. Nevertheless, there's some experiments that we showed. We have an encoded model prompt. We generate noisy samples, and we hope that if the noise is little, right, and we generate those embeddings, and then we generate the weights with the decoder, and we hope if this noise is only a little, then the weights will be similar to each other and also good in performance. If we add a lot of noise, the model should be destroyed. And the second idea is, how much can we interpolate from different models? Think about, we have two trajectories. We hope that we can interpolate between checkpoints of the same model during training, but it should be more difficult to interpolate between totally different neural networks in this space. And all, in the latent space that we then sample to real weights. So we did this. There's one result here. You can see on the blue is the noise level. So there's a population of models that we sample. We add a little bit of noise, and the weights here, the x-axis is the latent, the y-axis in blue is the weights. The more noise we add, the more different the weights that we decode are. So that confirms that our latent is well behaved in some epsilon. And also for each of those populations, we measure actually the performance. So the more noise we add, the worse the models are getting. Surprisingly, some models are getting better if they're a little bit out of the latent, which confirms that there's we could explore the latent. There's some space, some points in this latent that generate better models than the original model prompt. So that's this experiment. And the second one, when we interpolate within a model, that when we interpolate from checkpoint or epoch 5 to epoch 25 and generate models, the accuracy of those models increase. And when we generate models by between different arbitrary models, there's no well-behaved space in between. So that's great. So far about what we see here. Let's jump to the end and to the GeoSANE results. So what we have here, we have first of all UMAP visualizations of the trained latent space. So for GeoSANE, we see on the left, for example, here, on the right, the modalities. So you see a big group of models that are Lancet trained. Then a couple of, a larger group, the blue ones are Sentinel-2. Within that, you see some of those RGB only trained models. There's some separated cluster that is only trained on SAR, synthetic aperture radar, and there is some cluster of others. What is interesting is if you would look at these two clusters here, you might think, okay, they are both trained actually on Sentinel-2 data, but why are there two clusters, not one? Well, you have to look here on the left. The models on the top here, these are ResNet 50 models trained on Sentinel-2, and on the bottom here, these are the ResNet 18 models trained. So the latent space is doing something useful and something meaningful, as we mentioned in the very first slides. We see here a lot of swim transformers. Here we see some UMAPs, and here we see some VITs trained on other data, and the kitchen sink of VITs trained on Lancet data, or some VITs that are trained on Sentinel data here, and some VITs that are trained here on RGB data only. So there's a meaningful setup that we see here, which is actually really, really great. When we go into results, we compare it to training from scratch. So these are the different data sets that we have. Here we have the different backbones, swim transformers, or VIT large. If you train from scratch, you will get this performance. If you sample a model and use the same amount of fine tuning, you would get better models. So that's, if you think about computational budgets, you could improve the generation of models with the same compute budget as compared to random initialization, as sampling from our GeoSANE setup. You can also see that those are the numbers that are at the end of 50 epochs, that when you compare training, blue is generated models and orange is trained from scratch. On two of those data sets, we are actually with very few iterations or very few epochs already outperforming the trained from scratch models. Here also, you sample a model with your VIT image, ImageNet trained model, do 2 epochs of fine tuning, and you're already outperforming the training from scratch. So that's, how does it perform training from scratch. Then we have here the comparisons to other remote sensing foundation models. Here's, some results that are reported in the specific papers where we compare to others. We're not outperforming everywhere, but we are able to, so here what you see, we are able to generate, different from the same representation, different architectures, right? So for classification, VITL or swim transformers, for segmentation, so we can, go for all of those different downstream tasks and are comparable or able to outperform the foundation models on the reported, performance and single label, multi-label classification, segmentation, object detection, or on GeoSANE, we're also able to outperform or be very close to latest state-of-the-art models. I guess TerraFM was just, accepted at iClear. Took them, I guess, 12,000 hours to train. GeoSANE trained, for 300 hours or GPU hours as compared to some of those models. So it's very efficient because it's using the weight distribution of the Hugging Face models. So here also comparable and competitive to other foundation models. The big advantage of our setup is, however, we can sample small models. If somebody wants to have a small model, we can sample a big model if somebody wants to have a big model. So this is here the results. We used for those data sets 2 setups, one setup where we sample 11 million parameter model, here efficient at a very small model, and we compare to magnitude pruning, variational dropout, and knowledge distillation on a VIT large on trained on ImageNet or two foundation models that are very known, and then how GeoSANE performs if we directly sample the model. And you see the results here. In all cases, we are able to outperform on those different data sets the individual models as compared to the different teacher-student distillation, dropout, or magnitude pruning. So if you want to have small models, you can use GeoSANE and sample the small model directly instead of getting the large model and distill, right? It's in one step and it's better. And if you're really, squeezing down to very small models, we also are able to outperform. We have some issues here with function map of the world compared to scale MAC. There's some performance, but in general, if you want to have small models, you sample small models. You want to have big models, you sample big models. It's all the same representation that you can sample with, always the same setup for all those different data sets. This was also my last slides. There, in the paper are much more, many more results. Just to summarize, the presentation here is about the idea to train geospatial representations from models and not data. There is a rich repository of geospatial models on Hugging Face. Why not using that? And the way to do this is to use weight-based learning or a representation backbone that trains on the underlying weights. And once we have this, we can use the decoder with a model prompt to generate geospatial models, do the fine-tuning as in every fine-tuning regime, and be ready for application. That's it. Are there any questions?
So thank you so much, Damian. And what was super interesting, at least from my point of view. I would say let's open to question. I remind you that you can unmute yourself or write in the chat. Maybe I can start with one question, if you allowed me.
Sure.
In the meantime, that other people think about their question. If you can go back to the slide at the almost very beginning where you were mentioning about symmetries inside the symmetries in the weight space. I was wondering, exactly these slides, I was wondering if are there only symmetries in layers, in a single layers, or if you also try the symmetries on different layers. So exchanging weights from different layers. This is more tricky, and I was wondering if there are some kind of relation on that.
Yeah. So here I only showed the permutation symmetry, but there are also scale symmetries where you could think about you have a ReLU, right, everywhere. Okay. So if you scale up in the positive, like if the input is positive, you can just scale up and then arbitrarily augment and then scale down 5 layers afterwards, and you would have a similar setup. If not, you're going below 0. Because
that's clear. I was wondering about permutation symmetries. So are they only intra-layer or also among layers? So if I permute weights of different layers, I think things are messing up very easily.
Yeah. Yeah, and that's a good question.
Okay.
I mean, the simple setup is what is mentioned here within the layer, right? Or
Exactly.
the convolution.
Exactly, within the layer.
I could, are there symmetries that are spanning multiple layers where something is happening here and something there? Like, no, are there subnets in larger neural networks, right? So this would be the idea. I would think yes, potentially this can happen. I mean, you could mirror, you know, parts of blocks of the network. I never saw this being used in some of the setups in weight-based learning. The idea here in general for many people that are doing, you know, a lot of interesting work is to use encoders that are equivariant that kind of break the symmetries and, you know, project to either invariant to the same point or to, you know, equivariant point. For us, we're using this in this augmentation setup, but I could think that there are symmetries in blocks of transformers. You could think about, right?
Yeah. Okay, thank you so much. So if in the meantime somebody else has some question, please, you can unmute yourself or write down in the chat. Also, people at Philab, I don't know, Ruben, you can manage that.
Yes, thank you, Cristiano. Thank you, Damian, for the nice, super interesting talk. We have one question from the room. Valerio?
Yeah, can you hear me if I speak from here? I
Yes.
go. Okay,
clear,
perfect.
clear and loud, thanks.
Okay, perfect. First of all, thanks a lot. Very interesting topic. So my question is that, do you think, or maybe you made some experience about it, but are there any bias about the model selection? So are you, for example, curating this aspect? Because you said that you just gathered this from Hugging Face, but you didn't think that you can, I don't know, just select foundation model, bigger models, bigger models. Do you have any hint about it? Thanks.
Yeah. That's a good question. So we did this for the first time for the remote sensing world, and we just tried to get everything that we could find on Hugging Face. We have, so for example, the TerraFM example is a nice one that I mentioned because the model was not on Hugging Face. So we checked it's not in our, model zoo, but we still can generate models, you know, that are in performance comparable. However, if you would scale that up to, you know, download everything, I could also imagine that maybe there are other models, not only remote sensing models, that fit this setup that are performing, that are helping when you train. So what we did here, we skipped that. We used actually a pre-trained model trained on many computer vision models, and then fine-tuned on those set of remote sensing models. And it can happen that there are biases in the data distributions. It could even be that, you know, there are effects that we until now don't understand. So I hope that, so what we're doing now is we're kind of creating this model zoo. We're trying to verify the documentation that is provided by whoever uploaded those models. There's also, like, you know, those 100 models is the subset of functional models that we use for, GeoSANE training. We have actually downloaded much more, but then you cannot instantiate and you do a forward pass, something funny happens. So, you know, there's a kind of a funnel of models you can download, check that are functional at the end that you can use as weights. So we have those quality checks, but there might be biases that we are not aware of that are somehow, you know, spillovers there. So that can happen. And, you know, we're now looking more into the data. We also want to release this models so other people might be able to find stuff that, you know, we probably would not be able to think about, and to kind of, you know, provide also a ground for other people training representations on that, because there are many different backbones beyond, or besides the one that we have, this autoencoder that we're using. Yeah.
Thanks a lot.
I hope that answers the question.
I had a related follow-up question. You already answered it partially by mentioning that you trained just on 100 remote sensing models. That's not model types, but like sets of weights, right? That seems like very few. But then you mentioned that it was you started from a model already trained for more general computer vision tasks.
Exactly. Yeah.
Well, a model trained for computer vision models. Sorry, and do you know how many models that model was trained on? Because I'm interested.
2000. Yeah.
Okay, but because still 2000 is very few, right? If your average input length is like several million parameters, it's crazy to think that just 2000 or just 100 sets of model weights already enable you to sample useful other estimates for new model weights.
Yeah, so those 2000 models are also like a subset of, we have actually downloaded 30,000 models and then, curated this 2000s for the computer vision model zoo that we have. We have this remote sensing model zoo. If you look, however, in, for the computer vision model zoo, there's a lot of large models that we have. And the weights, the sequences that we use that we consume, they're like, millions, if not billions of parameters that we have. So what we hope now, because there's two things, right? The more data you have, it's great, but we also observed in some of our works that if you increase like the other way around, if you increase the backbone, our backbone has now 900 million parameters. The one that I presented, GeoSANE. If we want to now scale up, because that's what we observe everywhere, that scaling up the backbone will result in better performance. What we see is that we have to increase the heterogeneity of the underlying model zoo to make use of this free capacity. So if we have a larger backbone and we use just more models, but not more heterogeneous models, it's not working as good or as well as if we increase the heterogeneity of the underlying model zoo with regard to modality, architecture, and task. And therefore, we needed to go from SANE, that was only working on homogeneous zoos, to this setup to make it working. Yeah.
So the added heterogeneity, you think actually, because you could say it makes the task harder, but in this case, it provides more diverse input, so it also increases the performance. So
it's definitely, it definitely increases the performance. However, I think it prevents mode collapse, because I think if the model zoos are not heterogeneous enough, then if the backbone is too large, the representation takes shortcuts.
Yeah. Okay, and then a more. Sorry if you were still explaining something. I didn't want to interrupt.
No. Go ahead.
Okay. So during the presentation, I was thinking, okay, but if you train 1,000 models, let's say, and then you train a weight space model on those 1,000 models, then that could be very interesting to, I don't know, study the latent space to get characteristics, but slightly less if they're all the same 1,000 models, at least slightly less to then generate just new samples of weights that just do the same thing, right? Because then you've just it's like a very expensive training for in the end obtaining the same thing. So the very practically useful thing is more going in that direction of being able to sample weights for models that do different things, or that get like improved performance, or that you have to train much less, or different architectures, or which is then at the end what you showed that you could do. So that's very cool. So how do you condition the model on saying, like you want a target architecture and for a target task or a target data set, and then you get that, but both the task and the data and the architecture have been in the training data, or how does it work exactly, this conditioning? Sorry, long.
No. It's a very good question. So we have, like, if you compare the original idea that I showed you to explain this, right? So here I said they're all trained on the same data set, same architecture. When we observe same data set, same architecture, and just we vary the seed, large backbones collapse. If we have different hyperparameters that are going with different learning rates and different optimizers, it's helpful, but we cannot scale the backbone just by having the same architecture, same data set, and therefore the idea to go to Hugging Face and just consider the weights as data inputs, and the more, the better, right? So that's the one idea. The second idea is here, the conditioning. This is actually very interesting because until now, the conditioning is done entirely, like the architecture conditioning is done through the model prompt. We have another paper currently in review where we changed to data prompts, right? Instead of using a model prompt, you could think about using a data set, and this data set could be, through a data encoder being used to point into your latent. And you could train actually a model encoder and a dataset encoder simultaneously with their decoder, like, for example, Clip is doing, right, with text and image. So this is one idea. People did this already similarly, and we see that I think the future will be to condition the sampling through a dataset. And then it's going to be interesting because then the architecture is missing. The architecture here is done through the model prompt. And you could think about in the future, you take a model with an empty model, you use this as a conditioning for the architecture, you take the data prompt and you say this type of data for this type of model, and you generate. This is, however, giving a lot of burden on the decoder to be able to understand this. So we believe, or I believe that, we have to kind of give some information to the decoder what it is. This can be done on multiple ways. One idea would be, that we include not only the weight tokens, but also special learnable tokens or tokens that encode architecture characteristics. Like, hey guys, these weights are now fully connected layers, and these weights are now this type of layers, such that the encoder and decoder understands a little bit better that they are different, whatever they're doing with that, but that these are different types of layers. If you think about that, there are maybe a handful of layers or two hands of layers, and that's it. And you could condition that on those tokens, or you could condition the architecture itself. By one idea is, if you think about that, you could have like language models. They have the capability to translate in different or to generate different languages. And they are specialized decoders for the one or the other language. So I could think about having decoders that are specialized for different architectures. And then, whatever you prompt on externally what you want to have, you can then use the right decoder. This model here, GeoSANE, doesn't do that. That is all given by the heterogeneity of the underlying models here in this setup. We did some experiments where we tried to do some of those architectures that are outside, like the efficiency net, which we didn't actively run here in the setup, I think here. So, this type of model, it's still performing well, but, there are some not on all data sets, right? So here are also some ideas how we could improve that to get much better initialization or much better, weights for whatever task you want. And the task can be, large, small, different losses like segmentation, classification, or different modalities. That's the idea. I hope that makes sense.
Yeah. Makes sense. There's a lot of interesting future directions to explore, but
a lot of work to do. But I mean, the idea is really, and this is, I think, this is hopefully people would pick that up. Like, we do all this pre-training again and again and again from all this data. And why not doing pre-training from the weights? And then, whatever, you have in language models, you have pre-training, post-training, task-specific training, fine-tuning. Why not thinking in a similar way that pre-training would be, let's sample some weights, we already start in a good space and do like some fine-tuning with whatever data we want to use, whatever satellites will be there in the future, right? We have already a good conditioning or a good set of weights. So instead of pre-train from data, just, sample your model and do whatever you want. This would be really, really cool. And what we see is that, in the scope of the models that we found on Hugging Face and remote sensing, this works very well.
Yeah, very, very interesting. Is there a question online, perhaps, or? No, so far seems like no. Then, okay. I guess we can more or less wrap up.
Yeah.
Mhm.
Thank you again so much, Damian, for the super interesting talk. We're very happy to have you as a visiting professor, and hope that you can that visit may go through in the near future, and we can meet here in Frascati.